Okay, let's be honest. When you hear the word trigonometry, you probably think of dusty old textbooks, right? Maybe some confusing formulas. Well, I want you to forget all of that. Today, we're going to look at trig for what it really is. It's this incredible, visual story about how the simplest shapes create the most fundamental patterns in our entire universe.
And that whole story really kicks off with one simple question. I mean, what does a sharp, pointy triangle have to do with a smooth, rolling wave? They seem like total opposites, don't they? But you're going to want to stick around, because the way they connect is, honestly, it's pretty magical.
All right, first up, just a simple triangle. To figure this whole thing out, we have to start at the very beginning. Let's get back to the basics.
So what even is trigonometry? At its core, it's just what it sounds like. It's all about measuring triangles. Think of it as the official rulebook that connects the length of a triangle's sides with the angles inside it. And everything, I mean everything, we're about to see today builds on that one simple idea.
Okay, so let's look at a right-angled triangle. The names of the sides all depend on which angle you're looking at. See that angle we've marked? The side all the way across from it? That's the opposite. The one right next to it is the adjacent, and of course, the big one, the longest side across from the right angle, that's always called the hypotenuse.
So, how on earth do you remember all that? Well, there's this super famous mnemonic, you've probably heard it before, SOHCAHTOA. It's just a handy little trick for the three main functions. Sine is opposite over hypotenuse, that's the SOH. Cosine is adjacent over hypotenuse, the CAH. And tangent is opposite over adjacent, the TOA. Simple as that.
And using this is actually a really straightforward three-step deal. First, you just figure out which sides you already know. If you're missing one, no biggie, you can just use the good old Pythagorean theorem to find it. And then you just plug those side lengths right into SOHCAHTOA to get your ratios. Done.
Let's take a look at an actual example. We've got a triangle here with an adjacent side of 5 and an opposite side of 12. Do a little Pythagorean magic and bam, the hypotenuse is 13. So that gives us our ratios, right? The sine of our angle is 12 over 13. The cosine is 5 over 13, and the tangent is 12 over 5. For this one specific triangle, those ratios are locked in.
All right, on to part 2, the all-powerful unit circle. See, a single triangle is great, but it's kind of static. It just sits there. But the world around us is constantly in motion. So to capture that, we need to take our little triangle and put it into a system that's way more dynamic.
But here's the puzzle, right? One triangle only gives us, well, one angle. What about all the other angles out there, like 30 degrees, or 90, or 360, or even more? We need some kind of tool that can handle every single triangle we could possibly imagine.
And here it is, the elegant solution, the unit circle. It's just a circle with a radius of exactly 1. And that 1 is super important. It makes all the math unbelievably clean. Just think about it. Every single point on the edge of this circle can become the corner of a brand new right-angled triangle.
So our original triangle isn't gone, it's just found a new home inside this universal system. And as we move that point around the circle, we're not just changing the angle, we are literally generating every possible right triangle. All of them, packed neatly into this one perfect shape. How cool is that?
Okay, now this is where things get really clever. Since the radius, which is our hypotenuse, remember, is always 1, that SOHCAHTOA thing becomes super simple. The sine of the angle, it's just the triangle's height, the y-coordinate. And a cosine, that's just the width, the x-coordinate. So get this, the coordinates of the point on the circle are the sine and cosine. It's that direct.
Okay, we've got our points moving around a circle, we've got our sine and cosine. We are now ready for the grand finale. This is the moment we've been building up to, where we finally connect the triangle to the wave.
So I want you to imagine taking that circular journey and just unrolling it. Lay it out flat, like you're unspooling a ribbon into a straight line or a timeline. What we're going to do is track just one of those values, let's say the height, as the angle goes all the way from 0 around the full circle.
And there it is, the sine wave. And what is this beautiful curve? It's nothing more than a visual record of the triangle's height, that y value, as our point travels around the unit circle. It starts at 0, smoothly goes up to a height of 1, back down through 0 to -1, and then returns to the start. A perfect, endlessly repeating wave, all from a simple spinning triangle.
Now, this kind of repeating pattern has a fancy name. It's a periodic function, and its period, that's the length it takes to complete one full cycle, is 2 pi. Wait, 2 pi, does that ring a bell?
It absolutely should. That's the exact circumference of the unit circle. The wave's length is literally the unrolled length of the circle that created it. It's all connected.
Okay, so we did it. We connected the triangle to the wave. It's a beautiful piece of math for sure. But so what? Why does any of this visual magic actually matter in the real world?
Well, it matters a ton, because it turns out that almost everything that repeats or oscillates or vibrates can be described using these exact waves. This means trigonometry isn't just some boring prerequisite for calculus, no way. It's the fundamental language we use to understand sound waves, light waves, electrical signals, you name it. It's the language of the universe's patterns.
So, the next time you hear a piece of music, or see the light coming from your screen, or just notice any kind of rhythm in the world around you, I want you to remember where it all comes from. It all starts with the simple, elegant rules inside one little triangle. So my question to you is, what repeating patterns are hiding in plain sight in your world, just waiting to be described by a simple triangle?